So again, thank you for attending. Welcome. And this is going to be the GD&T Challenge webinar and dealing with the first challenge. Myself, I have been involved with other organizations that have done competition, both state and national levels, dealing with product design. And sometimes it's challenging to put a challenge together and doing the due diligence to make sure you only get one final outcome. And sometimes being involved in those competitions, those of us writing it know what the solution is, but sometimes we don't capture the correct wording. So I'm just kind of, this is my attorney talking inside myself, kind of saying, hey, you know, there may have been assumptions. So everybody, here's the what we call the weld flange assembly challenge. And we did have requirements, and I would like to step through those requirements before we start getting into it. So it was dealing with what we call a weld flange assembly, and these are two components that are machined elements that then get welded within an assembly, but it forms a mechanical joint. In this case here, we had what we call the male flange that was going to be assembled into the female flange over here. And there was a mating interface. They come together, and then we had a pilot diameter fitting into a hole that locate the components. And then the assembly was two bolt flanges here. Now, this is one that I've kind of put together, but this is truly mimicking components that I had dealt with at one of the companies I had worked with. Now, it didn't look like this. This is definitely modified, so it's not in competition. So I came up with this little two bolt flange. It was more than two bolts that we were dealing with. And there were certain things that we did have in this assembly that I didn't show. And I'll speak to them a little bit here, a couple of slides coming up. So let's review some assumptions that was going to be based on. So the Convention of Dimension and Tolerancing was going to be based on the ASME, the American Society of Mechanical Engineering, Y14.5 product definition standards dealing with dimensioning and tolerancing. So it's going to be based on 14.5. And the units, taking a look at this, was going to be based on US customary inch system, even though products could be done in either the inch and or metric. I didn't state these are assumptions that we're applying since we're talking GD&T. So based on that, I just want to kind of cover some rules that the reason being is that there were some submissions here and they were talking about this. So we do have rules in the 14.5, and I'm stating it per the latest standard, which is currently 2018. So paragraph 4.3.2, we do have rules depending upon whether inch base or millimeter base. And so I just want to comment here that, you know, the following shall be observed when specifying decimal inch dimension on drawings. A 0 shall not be used before a decimal point value less than 1. So these are just some of the conventions and rules that the drawings that you were looking at were based upon. So just, you know, putting a stake. So in other words, if it gets smaller than a whole number and you down into less than one inch, then those dimensions are going to just be a decimal point with a significant number of digits after it. In other words, it's not a leading 0, okay? And that's the rules that we're going to be invoking and applied. That was used on the handout sheets that was put together for the challenge. Next thing here is stepping through. So this is going to be the first of the 3 challenges dealing with this mechanical bolted flange joint. So in other words, there's going to be 3 things I'm going to be asking, but you're only seeing the first one now. And there's going to be more challenges coming out, and we're going to look at this because I'm going to ask for more requirements. So right now, the thing was to study the design intent in the dimensioning schema as shown. In other words, as provided in the sheets that you received. Then here, we're kind of making a declaration. The fasteners are not key locating features. So in other words, what we're saying here, other than, in this case here, they would take rotation away, But the main thing really is to, hey, bring these two mating features together and just apply a clamping force. And that's really the main intent here. What winds up truly being the locators is the actual pilot diameter fitting within the hole. Those become the real functional features. And a way to check, you can just see, hey, possibly what is the relationship on size compared to what we're doing up here on this mechanical joint? Which one would be the true key features? So in this case here, we're trying to tell you that, hey, in this case here, the fasteners, all they're doing is clamping the two together. Yeah, then they would stop rotation, but you notice that in this assembly, I could take these flanges and rotate them 180. There's no design intent. There's no clocking element. That's based on design intent. So we don't need that, other than two bolts will hold the assembly together. The other thing here in this challenge, we asked, determine what is needed within the feature control frames. Notice the feature control frames were empty. And we're asking you to take a look at and then determine for both the clearance hole and the threaded holes. And there was a requirement without changing any of the given dimensional items. So in other words, we're making it clear, whatever is already given, that can't change. That's what we're asking you to do. Leave it alone. Engineering has already made a determination. These are the values we want. So those were off limits at this point in this challenge number 1. Then there was another requirement that, hey, dealing with the fasteners, that they were going to be 1/4-20s, UNC, and they're going to be 1 inch long, and they're going to be fully threaded fasteners, even though the diagram down here, we're showing you what would happen if it wasn't, fully threaded. But in this case here, we were using fully threaded fasteners. So this default overridden what you were seeing here. Then we also stated, oh, by the way, use nominal. In other words, down here that you'll see that nominal size or basic. So we're putting as a declaration that use a nominal or basic fastener values if values are needed from the table shown below, and base values on 3 significant digits. Assume there's no positional error between the head of the fastener and the threaded feature. So right now that we're saying that ignore anything that could be happening in correlation to the head and the bolt. So right now we're taking them off the table. They're not part of this discussion. Now, if you were doing a joint, you may have to worry about that. But right now, these are the declarations we're making. Don't worry about it. Assume that the head and the body axis are in line with each other. That's kind of what we're saying here. So here, use the requirements and the information provided on the 2 views that we provided with the male and female parts. Determine the required tolerance of the mating features to ensure the parts assemble correctly and provide manufacturing the most allowable variation. So in other words, based on what you're seeing here, how can we not change anything, but give manufacturing as much allowable based on certain parameters that engineering would take a look at and pulling this joint together. So the joint must assemble. So in other words, it's always got to go together, no interference fits, and your answers should be based on equal tolerance distribution between the mating features. So in other words, as you're going through this process, we want to give equal distribution to both the feature control frames. So if you look at, we do have formulas. I'll be covering those here coming up. And the standard speaks to those, and they talk about distributions. And right now, I've put a stake in the ground. I only want you to do an equal distribution. Yeah, there could be other methods, but we chose to do this. Do an equal distribution. So those were the rules that we gave out on this requirement. Now we could take a look at it. So now we can break down and start taking a look. What did we know? What was given here? And I want to step through here. And the first thing I typically do is try to get my bearings. In other words, what are my datum features? What's the relationship? And how are we controlling those datum features here? So this is where we're going to break it down. Those were already predefined, okay? So in this case here, you can tell right away that there's a datum precedence going on here. You know, that right now is that we're calling out this one plane of surface here as a primary plane. Because right now all we have is a form control on how flat or the points in the surface has to be within the tolerance zone. Then hopping over, in this case here, to the pilot diameter, it then has a relationship back to A. So you can see that this starts to become a hierarchy here, and then this has a requirement that it must meet while we're establishing a relationship to data feature A. And the intent here then is, okay, what do we need to do dealing with here? So notice up here that the hole size and the limits of variation, the plus minus, has already been determined. And right now we're saying you can't change these, right? They are what they are for this given situation for challenge number 1. Same thing when I hop over to the female flange, same thing, that there's a datum precedence taking place here. And your primary plane here has got a form control flatness on it. Now with flatness, you're going to get 2 parallel planes. The points of the surface has to be within there. And kind of like what I say that, you know, that you get 2 parallel planes separated the distance of what's given in the feature control frame. In the tolerance zone, anything goes as long as the points in the surface are within that. And then same thing here, the hole is then relative to datum feature A. And again, this becomes a secondary. So on both these parts, we're going to derive a datum axis in a relationship to the primary plane. And then up here, same thing. What do we do? And what should be up here in the feature control frame dealing with a threaded blind hole? And on this one, we got a clearance hole, and that's where you're going to look at this as a complete picture of a mechanical joint. So now, with that being said, that kind of sets us up for the story, and there's some things I want to talk about first about, and it's a little bit more than this challenge, that these are the things engineering has to do. So in this case here, that they came up with, they had a flatness requirement here, and they came up with 3,000s, and they used the rule of thumb saying, well, a rule of thumb, how flat do you keep a surface here? And you notice the length of this flange, it's approximately about 3 inches, maybe a little bit more. So what they wound up doing is basing that the flatness is about 1,000ths per inch. So over this length here, they kind of picked the producibility of 3,000ths flatness. And then the relationship of the pilot diameter fitting within the hole relative to this. So let's take a look at this. So here we have this. So let's first talk about this one here, because the reason why I'm pointing this out, I did get some feedback and talking about, hey, if I take a look here, is there a problem that datum feature B, because of the extreme boundaries it may come into, actually override datum A primary? Yeah, it could possibly, because when you start taking a look at this, right, what winds up happening here is that if you do derive this here, kind of think of it this way, if I was to bring this flange into contact with the datum simulator, or TGC, I'd hit upon the high points here. In this case here, then the variation would go into the part. Well, some people just look at this and just think that, well, the plane can just tilt this way or can tilt that way within the zone. Well, your worst case could possibly something like this. You actually could get a crown in here and maybe get what the standard refers to as a rocker, or you can have some variation here. Now, engineering, that's where they're going to have to decide what these values are. Now, in this design, I did leave off a component. There is a gasket that really fits between these 2 flanges when they come together, and that gasket would absorb the difference of what the surface variation could be. So believe it or not, there was another material, but I didn't want to get this problem so complicated. So the reason why I'm speaking to this, I've just gotten some feedback from people that are engaged and did the challenge. So dealing with the flatness control, this is some elements that engineering would have to consider. Right now, I just threw a flatness on it, but there's things engineering could have done to minimize this. Now, I personally have experienced this. I had a vacuum chamber. My vacuum chamber door was 4 foot in diameter, and I had an O-ring compression seal. And when the machinist was machining the flange, the door, in his process, I asked to go down and qualify the sealing surface. That one there was, it was 24 inches in it was 4 foot diameter, 48 inches. And I had to have a flatness of 5 thousandths due to the compression O-rings we were using. So when I went down and inspected what the machinist had done, I had a requirement of 5 thousandths, but when we actually measured the surface, it was within 1 thousand. I was like, wow, I'm pretty pleased. So I said, okay, finish up machining and send it on its way. A couple days later, I got a call from inspection, said, hey, Ed, you got to come down and take a look at this. When I got down to inspection, they had my cover of the chamber up on the surface plate. They go see how flat it is. When I went over there, I went to rock it. Well, I could rock it. It wasn't supposed to be a rocker, but it was a rocker. And it rocked within about 1/8 of an inch. I needed it within 5 thou right away. And we did try to test fit it to see if the bolts would compress it. It would not compress. We had a problem. And so we had a process problem, we dealt with it. But these are things engineering would have to deal with. So engineering could have done different things, like they could have done an application of unit basis, something like this, which then controls, here's your max flatness, and they could have done a unit basis, which means that anywhere along this bar here, they're controlling the variation at any given point, not to be more than 0.2. That could be an option. I've done that. Or you can put other requirements like state a requirement to the feature control frame. So the standard does allow for like line elements, radial elements. So this is just another requirement saying that in this case here, the tolerance zone is still the same, 2 parallel planes, but all of it goes into the material. Now, yeah, you can get contacts in the fringes. This becomes a stable, repeatable datum reference frame. It's not a rocker, but it may still leak if this was a fluid type application. So I was just addressing some of the comments that I've seen people submit into that these are things engineering would have to consider. How do they handle that? Same thing over here. We got the same flatness control, same issues, same problems. So what winds up happening is here's a same thing, that if this is a hogged out machine part, depending on how this flange acts, yeah, you can get some distortion in there. You know, the tolerance zone is 2 parallel planes. What happens if this one comes in this way? Well, that may not be good, right? So when I bring the assembly together, here's my theoretical perfect mating, nice planar features, all the points in the surface perfectly coplanar, nice linear. And then if you had this type of a joint coming together, you want to tighten this up, might be an issue, might be a problem. Again, that is design intent that engineering would have to deal with. And how are they going to control these primary features here? And how do these secondary features relate to the surface variation? So that was just my attempt to make an attempt to explain about the datum precedence and how we're doing this. Now, again, everybody here, I believe Wendy is taking you off her open mic, that if you have any questions or concerns, that, you know, please feel free to speak up if you want to. And, oh, so it could go the other way, and, you know, you can have these, you know, stable, but again, you could have variation in the sealing surface. That's why in the real mechanical design, there's a gasket in there that compensates for any of this variation. I just left that out and didn't make it part of this design. Okay, now let's start stepping through here. Let's take a look at feature control frames. So in this case here, we're looking at the clearance hole, and this is what we're asking you to do: populate what the feature control frame would be on the male flange. And then on the female flange, dealing with the threaded hole, populate what needs to be in the feature control frame. So in this case here, when we start taking a look at them, well, here's what we got to do here and here. This sets up a relationship of a mechanical joint. Some people just look at the features and deal with just features, but really what it's about, you got a system requirement of a collection of components coming together within an assembly. And this is where GD&T really does a great job of doing mating relationships. And how do you control them? We have formulas we can do that with. So what goes in the first cell of the feature control frame? Well, that there is definitely reserved for the geometric characteristic, and I think I had no issues whatsoever. Everybody wound up throwing in position. So there was no problem there. What was the appropriate control based on the call out here? So there's no problems here, so that was good. This next one here, what's next? What do you have to answer the question here in the feature control frame? Well, once you're in the tolerance part of the feature control frame, what's the shape of the tolerance zone? Okay, what do we do here? Well, what kind of features you dealing with? Well, you notice in this case here, let me get my laser pointer up here. You're dealing with cylindrical features, right? You got a clearance hole that's round, you got a threaded feature here, tapped hole that's round, and we're gonna put a bolt in that's round. So in this case here, there's 3 types of tolerance zones, right? You have the cylindrical tolerance zone, you have a spherical diameter, and then if there's nothing here, it's a width total. So in this case here, everybody, I think I got this right. I can't recall looking at this that nobody got that. Now here's where what's next? What value should go in here? So in this case here, you got to ask your question, what's the tolerance requirement? Well, do you remember I definitely put a stake in the ground? I said, well, I must assemble. So whatever the value put in here, these 2 components, the clearance hole. Oh.
Did you eat?
No. Well, yeah, I had breakfast.
Oh, so what was the question, or?
Hi, Ed. I think I had unmuted somebody and they didn't mute themselves, and we were hearing a conversation in the background. So I think you could keep going.
Oh, okay. So the requirement is that must assemble. In other words, the bolts are always got to go in a hole when I bring these 2 pieces together. And oh, by the way, the tolerance on these should be equal distribution. So the value should be the same, is what we're alluding to. So how do you do this? How do you derive that? Some of the companies I've been at, I can quickly start looking at drawings, and here's what they typically do. They throw this number in there, 10,000. And I'm like, and when I query them, I'm like, okay, you do have a number. Where did this come from? Well, Ed, back in the plus minus days, we would typically default plus minus 5. And since we're doing cylindrical zones now, we just took the plus minus, turned it into a total 10, and that's the tolerance. Well, you did derive a tolerance, but some of the requirements was, does this allow me or manufacturing the most variation and assuming that allowing assemblability? Yeah, you're gonna find out this number is kind of small, that we could have allowed manufacturing a little bit more because some of the rules that we have in the standard. That would this work? Yeah, but you took some tolerance off the table for manufacturing if you just jump right to this number. Okay, but I can't tell you how many times people default back to the plus minus world and just convert drawing block tolerances and start throwing them in the feature control frames. So I've seen that. It's not illegal, but you're going to find out, hey, I took some tolerance away from manufacturing. If you really make the true assessment of the smallest hole, how much variation the threaded feature goes with the bolt coming in here. So that's what we're looking for. We need to still meet design intent, but yet give manufacturing as much tolerance as possible to meet your design intent. So in this case here, there is a section in the standard of 14.5. It's called Appendix B, and we have formulas for positional tolerancing. So we have some defined rules, and if you utilize these formulas, you're going to find out that you can prove out mathematically where things can be and be compliant. So with that being said, the appendix presents formulas for determining required positional tolerance, or maybe you already get the tolerance, then you can figure out, you're going to find out what I call contributors. You have a whole bunch of features, clearance holes, threaded holes, the bolt size, all come together in the sandbox, and they got to all play together. And the intent is, playing together means they all got to assemble. I don't get production line stops. So what's the required size of mating features to ensure parts assemble correctly? So there are formulas. One of the formulas deals with a floating fastener case. And that's a unique situation. You deal with clearance holes, you drop in a bolt, and you put a nut. And that's what we call floating. Then we have the fixed fastener case with projected tolerance zone. So that right away is that we're capturing one side with the fastener in one of the mating features, like a tapped hole. That's what we call a fixed fastener. Then we have other formulas here, tilting of the axis of center plane. When you don't use projected tolerance zone, it's a more restrictive formula to calculate out. And then we have coaxial features, if you're doing cylinders and the datum features and things like that. Then we have also one more, limits and fits. But we're going to focus on, in this case here, what do we have here? We're going to find out, this is the main one we're going to look at. So this is the type of fasteners. So with that being said, you're going to find out this joint, what the standard calls it, is a fixed fastener case. You got a bolt being threaded into a feature. In other words, you can't move around. Once you thread this in here, the bolt is where it is. And then on the other mating feature here, you're going to have a clearance hole. So with that being said, let me show you what they look like. So in this case here, this is called the fixed fastener. We got our legend in the back of the standard that kind of correlates to the contributors. So in this case here, I have a component coming together. That's the male flange fitting into the female flange. And in the female flange, it's got the blind tapped hole. And on the male flange, we got the clearance hole. Notice that we have some legend here of what's going on. So in one case, you want to know what the hole at MMC, how small can the hole be? So you got that part of the contributor that you have to look at. Then what size of the fastener? Now in the standard, they say the MMC of the fastener. And I kind of alluded to where, in this case here on the fastener, I said just utilize the nominal values. So in this case here, that we're going to just pull it instead of the MMC size. If you were really looking at the tolerances of what that feature could be, in other words, the major diameter could be actually smaller for a class 2. So we're just going to use the nominal in this case. And then the positional tolerance is a total zone. It's a diametral zone in this case, since we're dealing with cylindrical features. So we're going to utilize this formula. So what winds up happening typically, what's the thing engineering starts with? Well, they have a requirement, the mechanical joint must be. They usually will then pick the fastener first based on a requirement, like, maybe shear, compression, torsion, based on some design requirement, and that's how they'll make the decision how big the fastener needs to be first, typically how it works if it's a new design. Then based on that, what would be the appropriate clearance hole relative to the fastener? And then for this number down here to derive your tolerance, this now becomes a question of, well, based on the process that's going to make all these features, what is the capability? So there's a little bit more going on with this formula that we have here. This is just showing you some mathematical formulas. There's a lot more stuff going on with engineering, making the decisions about these contributors in the sandbox based on a design intent, based on a system requirement. So far, so good. You see how we got there? And this is a standard formula. And you'll notice in this case here, we're going to split the tolerance 50-50, equal distribution we're going to give to the tolerance of locating the features within the given parts relative to their Datum reference frame. So in this case here, let's focus on the flange here. So again, so far we gotten up to, going to use position, and we definitely is going to be a cylindrical tolerance zone. So far we got to the same here. So utilizing this formula, what do you already know about this? Well, there was already information given in the handout here for the challenge. You know what the bolt size is. It's right here. That's the tapped hole. Now in this case here, this 250 is a nominal value. Kind of think of it as a placeholder. Now what controls the tolerance on that? It's the class fit over here, 2B. But remember I told you just use nominal values when it comes to the fastener. Then we come up here for the hole. That's what we got to populate for H up here. What is the hole? Remember, a hole at MMC, so the smallest hole in this case. And we're going to try to figure out what should this value be. So utilizing the fixed fastener formula, which out there take the hole at MMC size plus the fastener. Now I just put the word fastener here, but the standard says fastener MMC, but I said, well, just use nominal. So in this case here, my hole at MMC 280, 1 nominal minus my lower limit gives me a hole at MMC of 280 minus the bolt. And here I said just use nominal values. So we're going to inherently have some variation built into this because of the size. But, you know, again, I said don't pay any attention to any other contributors on the bolt. In other words, there may be a straightness requirement. In other words, how bad can the fastener bend or bow? Yeah, right now, utilizing this, you are going to get a little bit of cushion because I'm going to tell you on a class 2B, the max diameter is smaller than 250, but not much. You know, the tolerances on threads doesn't really give you a whole lot. But there is some built-in wiggle room. Now I can solve the difference between these two gives me 30 thousandths, and we wanted to do equal distribution. Then what do we get here? 215. I mean, I'm sorry, 0.015. I was looking at the 2 here. Sorry about that. So in this case here, you would populate that with 0.015 to do an equal distribution here on this part. So that's what we're looking to do, dealing with trying to derive the value on the part. Now, I've seen that companies to where they may have some other rules or convention they apply. So right now I asked for the 50-50, but you know, I've seen to where at some companies they've done what they call a 60-40 distribution. In other words, you can turn this into a ratio, this 30 up here, and then give an unequal distribution. Usually what they do is they give a little bit more tolerance to the tap tools, because once you tap it, it's a done deal. And so they'll lean more. I've seen 60-40, 30-70, 1/3, 2/3. So depending upon the company, what they're going to wind up doing here. But we were very specific, just do equal distribution. So over here, you would look at, in this case here, you can get the hole. Now what I'm going to do here is, let's prove out mathematically is you know, we're going to check the collective effect. Well, how small can the hole act based on this tolerance with its limits of size? So we're going to be checking what we call a virtual condition size. So, or you want to call it inner boundary. In this case here, you can do a standard equation. These formulas are all in the 14.5, how to do these. So it's an internal feature. I want to know the collective effect of how small the feature can act. So in this case here, you would take the hole at MMC size minus the applicable tolerance it would have. And right now, we're just going to treat it at 15. In this case here, you do the math and you get it can act as small as 0.265. Now we're going to take a look at, let's do what the fastener would act like. So in this case here, how big with the fastener in there, external feature. lo and behold, that good to go. So this is just another way here. There'd be more information over here to calculate this out. So there's a checks and balance you can do to mathematically prove out everything's going well based on your design requirements. So now we have this here, right? So right now, coming up to this point, that if I don't put anything here, is that it's understood rule number 2 would kick in. In other words, if there's no modifier here, these are on what we call an RFS basis. So it's regardless of feature size, all manufacturing would get would be what's stated in the feature control frame here. So rule number 2, it's a default rule when your drawings are in accordance with 14.5. So remember though, the fasteners were not a key locating features. They're only clamping the flanges together. So determine the required tolerance of mating features to ensure the parts assemble correctly and provides manufacturing the most allowable variation. So the fasteners are not key locators. Provide manufacturing allowable variation. So what are we talking about here? Well, since they're not key locators, then allowing more manufacturing would be put a circle M here. This now introduces the MMC concept. As manufacturing makes the hole larger than its MMC size, they get additional tolerance. And that additional tolerance comes by the limits of size of the tolerance on the hole. So in this case here, the smallest the hole would be 280, right? Then manufacturing is only allowed 15 thousandths, but then as the parts its MMC size of 280 going up to its biggest hole size, which was the 281 plus 7 or 288, there's the additional tolerance. They can get another 8 thousandths of additional tolerance. In other words, the hole gets bigger, I allow it to move more. So this would be allowing manufacturing here. So I'd highly recommend that gives manufacturing more variation. What about down here? What about tapped holes? Now it's kind of funny, I've been doing this for a long time. For some reason, you know, going down here, do you put modifiers on threads? And boy, if you want to pull a pin on a hand grenade, go up to a GD&T log or blog, I mean, and query a question to the group. Should you put M's on threads? And you may get a plethora of different opinions here. Now, I will say this, the example shown in the 14.5, they have M's on threads. But I'm going to allude to, right now, my example here, I did not include M, but would I put an M on my threads? Yeah. So in this case here, you're going to see the solution here. There's not an M on the thread, but I'm not grading on that. If you didn't put an M or you did put an M, I'm considering both questions equal. Putting an M though, here for me, as far as I'm concerned, it's like I can build a hard gauge to qualify the tapped hole. Literally can build a gauge to show representation of that. And I'll have an example coming up here shortly showing you that. So with that being said, there could be an M here or may not be an M, depending upon companies' policies or practices. But right now, if you put an M here, I accept it as good to go. So now, past the material condition modifier for the thread, what do you think you would be the next thing you need to do with the thread? Well, it's a bolted joint. In other words, you got a threaded feature, you got to get the bolt through the clearance hole, through the cover, the plate. Now, if you kept the tolerance zone inside the material, in other words, the axis of the threaded feature, the tapped hole, is that if you just didn't say anything on the drawing, you left it just like this, then the tolerance zone is in the material. And what we're showing you here is that if you did keep it in material, this tolerance zone appears of the clearance hole. So you can see that if manufacturing did produce the hole and it tapered within the axis, or should tapered within the tolerance zone, the axis of the threaded feature could still meet the requirements, but yet when you project the bolt out, guess what happens? So if you didn't do projected tolerance zone, you could possibly have an interference condition. And
Ed?
what it is, yes?
Oh, I'm sorry. We do have a question. And it may be on slide 4, I'm not sure. It's on the nominal thread, about the nominal thread. Did you say to use the nominal size?
Yes.
Okay, thank you. That was clear.
Right. So that was one of the qualifiers that we had put on there, speaking to both. So in this case here, everybody sees projected tolerance zones when you're starting to do a concern of the tapped hole depth relative to the thickness of the clearance hole. There's a relationship here. Now those formulas that I showed you, those formulas dealing with either the fixed or fastener, they're basing the values that you are doing projected tolerance zone. So so if you use those formulas and do not use the projected tolerance zone, you may be at risk. Now, the question is the thickness of this part. If this was a very small sheet metal part, do you need to do that? And that's a question engineering needs to ask themselves. When is it appropriate to invoke the Circle P modifier? And if you are dealing with some substantial cover thickness here, so in this case here, if you keep the tolerance zone inside the threaded hole, you definitely see the axis of the bolt can act bigger when you thread this fastener in. I don't know if you ever experienced this. I have, sorry to say. I'm threaded in my fastener. I can feel my bolt start to thread and then it stops. What's happening is I got it to start, but because the actual tapped hole is tilting, now what's going to happen as my bolt goes in, I'm going to start cross-threading and doing damage between my bolt and my threaded hole because my clearance hole is limiting how much tilt it can do. It may not compensate. So in this case here, if you're not going to do the projected tolerance zone, you better give me a more ample. And that's what the formula is for when you don't use the projected tolerance zone. You're going to wind up either really tighten this tolerance zone up, or you got to make the clearance hole at MMC much larger. Pros and cons. If you do use the projected tolerance zone, what happens is that the tolerance zone is no longer inside the material, in other words, where the tapped hole is, you are projecting it outside. So it kind of looks like this. The tolerance zone is no longer in the material where the tapped hole is. You are projecting it from the outside surface out. So that's what we're looking to do. So this is the tolerance zone for the actual axis of the feature in the material, but you're controlling the collective effect of what it's acting like when it protrudes out. So that's what we're alluding over here. So some people did not pick up on this, that Circle P projection tolerance zone. And the reason here, take a look at how thick the flange is, the tapped hole relative to the flange up here. So there's a good ratio that this flange is a little bit thicker than the depth of the tapped hole. Notice over here the depth is 1/2 inch min, and over here the flange thicker. I would absolutely be doing projected tolerance zone in this fashion. Or you would have to use the formula of not, which means these numbers would get really tighter, believe it or not. Not allowing more variation. So here, I just kind of threw this in Tec-Ease. We have tips of the month, and back in 2003, tip of the month that was talking about there is a place for MMC on thread. So this is a nice little tip that was put together here back in 2003. Many people believe that since threaded features generally center themselves on the threaded hole, the MMC, max material condition, is not applicable. Well, MMC is needed on the threaded features to legitimize hard gauging. And that's really what I do when I'm putting my M's on here. It's not so much to take advantage of additional tolerance, but I can literally build a gauge to actually check this. Now what we have here is 2 single segments, and the gauge is going to be dealing with this one right down here. So using MMC, however, does allow the use of hard gauging to verify position tolerance, even when the projected tolerance zone is applied. So here, what winds up happening is, here was my part. I can literally build this gauge to wind up and drawing below in the gauge that could be used to inspect the projected tolerance zone of the M10s. So again, we have this tip that's showing that here. But I'll tell you, man, for some reason, putting this M modifier on threads, some people have some real heartburn on this, just FYI. So the standard does allow it. So engineering, it's their decision. And there is thread and gauge elements you can come in and put on your features here and project them out if you didn't build a gauge. So there are things you can do to do that. Now, how far do you project it? So here we're looking at that, well, what's the bolt have to pass through? Well, it's got to go through this clearance hole up here. So what's controlling the thickness here is the value of the flange. And some people, I did get some information, or some people missed this totally and just left the tolerance zone in here and just did the 15. So over here, how does that work? Well, the design intent is to ensure parts assemble correctly. So in this case here, use the maximum thickness of the flange for the projected tolerance length at a minimum. So typically what happens here, so if you came up here, I got a nominal value of 0.562, then add on the thickness here. So put the minimum in here. So inspection at a minimum, they have to do it. They want to project it out further? Okay. This is a minimum requirement that you need to do here. Okay. Some people here just went and did 0.6. At least you're further than, and that'd be okay. But here, this just kind of really states what is the minimal requirement here that they need to do in this case. So far, so good. No questions, concerns. Everybody's pretty quiet. So what comes next? Well, what's my datum reference frame here? So in this case here, that how are we going to mount it? How does it actually fit in the assembly? Well, I definitely have a primary plane A here that we can wind up doing. So that's how the assembly's coming together. What's the mating conditions here? So in this case here, it's going to be flange on flange. We don't want this to leak. So that's my primary. Then next here, what's next? B. But now B is a feature of size. So in this case here, B and an MMB. So in other words, what's happening here is that if the datum features are gonna depart from its MMC size and goes towards LMC, there's gonna be a little bit of clearance between these two mating features. Then we can allow these features to take advantage of what we call additional shift. So if the features go from MMC to LMC a little bit bigger, I can allow a little bit of movement, shift. So here's what we're looking for. So you see in the end solution here of what we're looking for here. Now, in this case here, just to let everybody know, if you didn't put an M here, okay, that was good. If you put an M here, that was good too. So and in the solution here, I just left the M off. In other words, alluding to if you didn't do that part, you're a little bit more restrictive compared to putting an M in here. So that was my only thing that I kind of alluded to. So this is what we're looking for. So that was the solution to this problem here. So the end. So with that being said, any questions, concerns, disagreements? What do you think?
Hey, Ed.
Yes, sir.
back to the projected tolerance.
Okay.
I could just ask you, how do you dictate what side to project?
That's a good question. Now, in this case here, being a blind hole over here, I can just put the projection right in the feature control frame. If this had been a through hole, then what the standard says, I could come up here and put what we call a chain line on the side I want it to project out, and then you can actually put that dimension. See this dimension here, 0.592. I can put it over there and show you which way that, using that chain line, you project it this way or you would project it that way.
Okay.
On the standard. Now the standard, if you're dealing with MBD world, if you're, let's say you don't have a drawing, then the MBD, what you got to do with the leader line has got to touch the circle on the surface of that side you're projecting out. So the 41 has a little bit different rules than 14.5.
Okay.
Just FYI. And there's a new one coming. Well, I shouldn't tell you that. We have another standard that they're doing something a little bit different. We call AED. They're going to do a little bit more changes dealing with this projected, but that's right now in a draft state, so I really shouldn't talk to it yet. It's not official. But what do you think? So that was a good question about the projection tolerance zone, equal distribution, anything like that. So these are the challenges. Now, this was challenge 1. We're going to take this problem, the solution here that we're looking for, and challenge 2 is going to come out, and we're going to then take the same part, and I'm going to ask you different things now about how we can take more advantage. So challenge number 2 is going to be looking at the same problem, but I'm going to have different requirements, and how do you implement that? So that will be coming out. Wendy, for challenge 2?
Yes, that'll be coming out today. We will post it after this webinar is over.
Yep. So we're going to develop, there's going to be 3 challenges based on this given problem. In other words, these flanges, and I'm going to be asking different requirements moving forward. So right now we just did an equal 50-50 distribution in this case here. So you're going to start with this now. So challenge 2 is going to bring this one in, but I'm going to have a lot more different requirements and opportunities to see what we can do to allow more variation. So any questions, concerns anybody may have on what we're dealing with? What do you think? Good to go. Everybody was quiet except for that one unprojected.
So what if you back up one slide, Ed?
One more, or this one, or?
No, that's it. That's good enough. So figure 3, where you get the position's perpendicularity on Datum B.
Yep.
Yeah. Could you put a control of position, or should you, or is it correctly with perpendicularity?
Well, let me say this. There's not an example in the 14.5 when it's a secondary datum axis, which really winds up controlling location. In other words, what it comes, this derives a datum axis that has an orientation to A. So there's no real location of this feature. Why? Because it becomes the primary locating datum. So depending upon what companies you're at, the standard, we don't show any example where we put position in here. We consider this just an orientation control. Now, has companies put position in here? Because they say, well, with position, I control orientation. I've seen that, but I can speak at aerospace companies. We have some very rigorous people reviewing the technical drawings. They would redline that position out and they'd mark it up as an orientation control only. So depending upon your company, the standard does not show anything along those lines when it's just an orientation. But some people say, so I don't know if that helps, Depends
No,
upon.
that did. Thank you very much. No, that I see what you're saying because you just got one primary datum.
Right, right. But
Mm-hmm.
have I seen companies put position here? Yep, yep. Now,
Yeah.
me myself, I could look at that and I can extrapolate. Oh, yeah, they got position, but really the only thing that's going on is an orientation control. So it really doesn't cause me heartburn in that case. That would I mark that drawing up? Probably not. Oh well, let
I
me
just
say
didn't know if
this.
it's. Yeah.
So if I was at aerospace, I may mark it up knowing what we have to get it through the checking group. So
Mm-hmm.
we had some
Yeah, I just
pretty.
didn't know if it was wrong.
What's that?
Like, I was just curious if the Y 14.5 stated, by putting position, is it wrong?
They don't speak to it at all, as a matter of fact.
Okay.
That's what
All
I'm
right.
trying to say. But
Yeah.
but if you look in the words in the standard that they say, oh, with position, you control orientation. So some people expand that concept saying, well, I think I can do both and be legitimate. And so that's kind of where
Okay.
my opinion.
No problem. Well, thank you.
Yeah. My what I try to tell my engineering groups, let me say it this way. I kind of approach it, hey, if we had to go into a court of law, and if I had some real attorney that was going to try to bloody my nose, I'd really probably like to keep it orientation, just in case there was some debate. So how often does that happen? Not often, but I do have a friend of mine that for the last 2 years, all he's been doing is litigation. He's a subject matter expert, and that's what he's been doing is for the last 2 years, testifying in the court of law, the meaning or intent of dimension intolerance on product definitions. So hopefully you don't ever wind up there, but just
Yeah.
FYI. Yeah.
All right. Thank you.
Yep.
Hi, Ed. I have a question. Do you have a time for that?
Sure.
Yeah. So if I don't use the projected tolerance, I understood that I should restrict the geometric tolerance of 0.015 with the formula. Could you please explain that how that works?
So in this case here, we're talking about the, I'm trying to get to this. So we're dealing with this projected tolerance zone?
Yeah, so if I don't use the projected tolerance zone, then I need to constrain or restrict my geometric tolerance 0.015 little tighter to bring this bolt into the perfect position. And if I understood correctly, you told that I need to use a formula for that. Could you please explain on that?
Yes, there is a formula in the standard in subparagraph B.5. So tilting of the axis of center plane when projected tolerance zone is not used, there is an equation. What they'll do in that case there, you'll have to pull in, you'll pull in mathematically what the thickness of this plate is, and then you're going to derive what size the actual cylindrical tolerance zone can be to ensure that you don't have this scenario. So what it winds up happening, it's going to really tighten the zone up really tight so that the tilt going up here is minimal. And the tilt, actually, so what happens, you see my axis of my bolt right now? Notice that it's outside my upper zone, which is in the plate, the green plate. The equation will take and tighten this tolerance so tight, that axis up here will stay in this boundary right up here. So in other words, you're going to see this is going to get really, really tight to keep the axis tilting within that zone. That is an option though. So there is another equation to do when not using the projected tolerance zone. Good question.
Okay. Yeah, thank you.
And the question is, matter of fact, I was just talking to somebody from a training class, and they're struggling. Hey, Ed, they're trying to figure out when do we use this projected tolerance zone. One of the companies I was at, an aerospace company, we ran a mathematical, or they did, and they pretty much came back, if I understood the white paper, that they said there's a ratio of the length of the thread of the feature relative to this thickness. And they said the ratio between the thickness of the plate and the thread engagement, once this starts to become a ratio of 65% or bigger, then you ought to start thinking about projected tolerance zone. So for example, instead of being this real thick part, if this was a thin sheet metal part, would I worry about projected tolerance zone? Probably not. In other words, it's well under whatever this thread engagement is in the thickness of the plate. In that case there, you may not use projected tolerance zone and stay with. So if this, instead of being this big, thick, 1/2 inch or 5/8 thick flange, if all of a sudden this went and I had a 1/4 inch bolt and this was like, I don't know, 30,000, 60 thousandths thick sheet metal, I would probably leave the projected tolerance zone off, because I don't want you to measure that short little distance of what we're controlling. The odds of probability, now again, it's like gambling in Vegas, what's the probability of non-compliance? So there you're dealing with producibility. But have I done that on sheet metal parts and not did projected? Absolutely. And it never really came back to get me. I ought to knock on wood on that. Watch it now, I'm gonna get burnt. So
yeah, thank you.
Okay, any other questions, concerns?
Yep, I have 2 questions for you, Ed, that people have typed in. One is, does datum shift apply here, and if so, how?
Yeah, so when we did, let me get over to the slide. So when we get, let me get to the appropriate slide. So when we did this right here, so we are dealing with that, this is what we call, so let me come up here. So notice that I have a circle M here. That's a tolerance modifier because it's in the tolerance part of the feature control frame. And for me to use what the term, the syntax call this, that's the tolerance modifier or the MMC condition. Now, in 2009, we introduced some new terminology and redefined. Now, we didn't change the symbols. These have been this way for, oh my God, years and years and years. But we were struggling with this modifier right here in the new term. So this one over here, we call this the MMC condition, right? So that's the MMC, the tolerance modifier, that I can take advantage of additional tolerance, bonus tolerance. This one over here now, my correct term I must use with this, we call this now the data modifier, or the modifier at what we call an MMB condition, max material boundary. So in this case here, so it's relative to what size did manufacturing make my datums. So in this case here, if I come over, so over here, you can actually take a look at if this feature comes in its MMC size, so it'd be 1.398. That would be the biggest diameter. Then, so that's right. Let me write this down. So apologize here. I'm using my mouse to write these numbers. Gets pretty ugly here. So there's my MMC, 1.398. If I come down to my hole, in this case here, my MMC of the hole, smallest hole tight, in that case there, 1.4 minus 2 thou, then lo and behold, guess what size it is? So the MMCs are identical. How much shift am I going to give when these two parts meet? There's not going to be any shift whatsoever. Now, what happens if manufacturing, they make this diameter smaller in size down to its smallest diameter? Well, that's the LMC size. In that case here, take the 1.396 minus 0.2. So now I'm coming in 4 thousandths smaller in size compared to this. So I'm coming at 1.394. Then in this case here, same thing over here, if I came in at its biggest, it'd come in at 1.42, or again, there's another 4 thou difference. When I bring these two together, that 1.402 with 1.39, I said what, 394? Is that what it is? Look at the difference now. The other ones were no movement at all. Now the variation here is 8 thousandths. So if these holes were off a little bit, or the tapped holes were off a little bit, I can now allow the part to shift or move. If you were to build a hard gauge automatically builds this right into the hard gauge. What we call datum shift, datum displacement. So really it's about what size does the datum feature. So, and also I gotta say this, and the features are very perpendicular. They're not tilting. They're very perpendicular to the primary datum. In other words, nice planar. Small diameter, very perpendicular. Big hole, very perpendicular. And then you'll put these two parts together. They can shift or displace. That's datum shift. And we're allowing that. And that's a good thing. We allow manufacturing more variation. So that was the whole thing about, yeah, make the parts, give manufacturing as much tolerance. So that's why we're looking for an M right over here. Oh, come on. Let me clean this up a little bit. So does that help? So by putting modifiers in, I allowed for take advantage when the holes got bigger, they can move out of position relative to the true position. Then depending upon what size the datum features came in at, I can allow datum shift. Did that help?
I think so. I'm not getting any other questions on that, so that's good. And then we have someone that has 2 questions. Go ahead and ask those. Joe, go ahead. Okay, I'll ask for you. His mic must not be working. Can you explain the 0 MMC tolerance on the perpendicularity control, or is that for another webinar?
No, that was just a not for another webinar. I mean, it's just something. In this case here, I'm trying to get my pen. So in this case here, we're looking at these feature control frames here. In this case here, I'm allowing as much possible variation for manufacturing. So in this case here, dealing with this pilot diameter, when it comes in at its MMC size, what's its orientation relative to the primary plane? Yeah, we're allowing no tilt. So if they produce the feature at its MMC size, which is 1.396 plus 2,000, so it comes in at that diameter, 1.398, it's got to be really perpendicular here. In other words, its axis can't really tilt too much, right? When it comes in its MMC size. So essentially, it's got to be perfect in orientation. Same thing with the hole here. Now this hole, it's got to get smaller down to its MMC size, which is 1.4 minus 2,000, or it gets me down to 1.398 in it too. Now, if I didn't make those at those, well, are these two features going to fit together? If I have a diameter that is at 1.398 and I have a hole that's at the same value, probably not. But what I'm hoping here is that manufacturing winds up centering up their processes here. So it's related to process capability, and I'm taking a risk. Now, I have done this on thousands of parts. I've applied 0. But let's say if I was not comfortable with that possibility, or the risk was high, probability of MMCs of both features coming in, I can inherently modify the limits here, so I automatically build in a gap of non-interference. So I can either readjust my MMC size of this here, make it smaller, a little bit smaller, or adjust it so that my hole doesn't get that small either. I can inherently build in. So that's an engineering decision. But have I done this on some of my designs? Yeah, I've driven it down to where it's 0. And you may have boundaries. If both parts come in at that, it might be a problem. Did that kind of help? So in this case here, at MMC, they're perfectly orientated relative to the primary. As they get smaller, they get more tilt. And again, what does that circle M means? Where does the tolerance come from? Well, it comes right off the limits of size. that's where your additional tolerance comes from. Sometimes manufacturing, when they see this, they panic. They like, oh my God, we got to make a perfect part. They triple or really up the cost of the part. And really, in this case here, this tolerance is tight, but where does it come? You don't have to make a perfect part. It's relative. Bonus tolerancing comes from the limits of size. So my fabricators, if I would hope that they may be focusing on a nominal number here, like this here. If they center on this, they center on this value, what's the odds of probability of them going both to their MMC size and then coming together? That's the risk I'm dealing with. Did that help?
Yes, it did. You hear me?
Yep.
Hello? Okay, great. Also, I see a simultaneous requirement sometimes in some hole patterns. Does that apply here? When do you apply above more than 3 holes?
Well, that's a great question, and I did notice that. I apologize. The drawings would have to be totally dimensioned. I didn't do that, but I did throw one here on the female flange. Notice that I have this profile.
Yes.
And notice that. Look at this here. The datums here on the tapped holes, A primary, B and MMB. Then the profile, A primary, B and MMB. These two are tied together because we have a default rule in the standard saying when you have the datum features with the same datum precedence, then this rule is automatically kicked in for position and profile, that the inspectors would have to qualify these two tapped holes and locate this back surface in the same setup. That's invoking what we call simultaneous requirement. So
and that means one gauge will inspect both feature controls.
correct. They'll have to do, and yeah, so in this case here, that they'll have to inspect the part, qualify both tapped holes in that planar surface at one time, simultaneously, okay?
At one time, but that doesn't mean that it could be 2 hard gauges or 2 gauges. Not necessarily 1 gauge, right?
Well, now what's happening here? Now in this case here, this is a plane that's perpendicular. It would not play into it. In that case here, there's no problem here. But if I had another feature that was coaxial to the 2 holes, then datum shift would come into play. Then you would have to have, then they have to do one setup, measure them all. They can't measure the 2 holes, take the part off, and then put the part back on, and then just measure this hole. That'd be 2 different setups, and that's not simultaneous. So, FYI. That's interesting. That might be a challenge question. Dealing with datum shift. Thank you very much. I think you just gave me a problem.
Yeah, I was wondering where this profile coming from. Where are you constraining? Great. Nice webinar. Thank you.
Good.
So Ed,
yes, sir.
Just a quick question. So with the simultaneously requirements, is that a good thing? I think that'd be a good thing, right? Because then the inspector has to only do one setup.
Yeah. But you're right. That's a requirement based on the rules. Now, if you didn't want that, what I could do in this case, that you could come underneath here and what the standard says, hey, Ed, I want these checked separately, even though I have the same date. You can come in and put in what we call an abbreviation. I apologize, my sloppy printing here.
No, I know, separate requirement.
Yeah, separate requirement, and put them on both. That now I can do 2 totally different checks.
Yeah,
now,
but
I could check them simultaneously if I wanted to. If they meet that, then I'm done. But if one of these are out relative to each other, then you're back to separate requirement.
I guess I'm talking, it's like why would I put a separate requirement? I mean, I would think it would be easier for the inspector.
Well, yeah. Let me give you an example. I had this happen. I had a cover going on a big electronic enclosure, and we had 4 fans we were mounting. So typical with the fans, we had 4 holes and 1 big cutout hole. And if I had used one datum reference frame like ABC on all 3 patents, now when the inspector brings that in, if one of the fan hole locations, the group moved together to each other, they move. In other words, the fan would fit, but yeah, to the other fan holes, I've now shifted. I'd have to disqualify that part because all the features must meet the simultaneous requirement. So this is why would engineering want to do a separate requirement? Well, those features have no relationship to the other set, break them apart.
Okay, that's a good. I see exactly what you're talking about. Thank you.
So actually, you just gave me another problem. Separate. So we could do one with datum shift. We could do one with separate requirement. These are really great, guys. I appreciate
it. No problem.
Yeah, and no, FYI, when engineering does do this, they put these M's on here. What the downside of this part can now shift and move. Now, by me allowing these 2 mating parts to come together, in other words, now this flange could come over here, it could shift. In other words, it can offset. Now, that may not be good in the design because I had a wall over here. This part just shifted. So this is something about when you start doing the shift, features are going to move and that. So engineering has to take that into consideration. You're allowing more possibly assembly shift, and that would have to be a design concern engineering would have to be paying attention to. So there's pros and cons, and that, again, it goes back to engineering and design intent. But I think just by you guys asking questions, I can come up with some great examples of, oh, I don't want it to shift in this, so we would not add modifiers on your datums. For example, I used to do work with missiles, and some of the missile joints, we'd put in 2 dowel pins that would fit the missile joint, and then the bolts were just for clamping. The key locators were the dowel pins. If I put modifiers on those dowel pins, they could shift and move. In other words, the outside diameters of the missiles could be shifting. In other words, they won't stay very coaxial. And my aerodynamicists hated when the surface might protrude proud on one side. It wouldn't, in other words, it caused drag. So there's design intent is what I'm trying to allude to, of why you would do these here. In this case here, it was no big deal. We took advantage of shift, possibly, FYI. Great questions. I love it.
Hey, Ed.
Yes, sir.
This is Jeff. I had a comment on the MMC on the threads. I guess I agree with you. I do it that same way. Put the MMC on to allow for inspection. I guess my comment was going to be you wouldn't want someone to try and apply a bonus tolerance to that, though. So,
right. Yeah. Jeff, do you have you dealt with anybody that tried to take advantage of that bonus tolerance on the thread?
I don't know of anyone like who has practically tried to inspect it, because that's really hard to do. But I have worked with engineers who have argued that, yeah, you should be able to include that bonus tolerance.
I ran across one particular engineer. He was a manufacturing engineer, and he was using it for that, Jeff. Mm-hmm. Hey, Ed, I'm going to allow that. No, and him and I got into a professional discussion, and I said, kind of what you just alluded to, Jeff. No, don't, because when I start, threading that up, it's going to self-center, and and him and I. Well, here's what happened, Jeff. We agreed to disagree.
That could potentially cause problems, because if now if you've got your thread at LMC size, and now you've added, you're at a position of allowing a position of 20. You're and you got a fastener that comes in at the MMC size, it's going to self-center, and now you violated your boundary condition calculations.
Boundary, and or you may start doing stress into the bolt, or
Yeah.
it goes on and on. So yeah, and you know, the standard, we show the modifier in the figures, but yet we don't add any verbiage in the 14.5 exactly saying what we were just saying, Jeff. I wish we did.
Yeah.
To help facilitate a clearer meaning of intent.
Yeah.
But I can say this, the committee doesn't like doing that because it's accepting some risk and say, well, the design engineers ought to know what they're doing. So we're not going to tell them how to do their job. But Jeff has, well, you're well aware, sometimes it doesn't go that well.
Yeah. I mean, I know, like with an external thread, you can do a measurement over pins to get a size measurement of the pitch diameter, but
right.
I don't know how you could practically do that on an internal thread. I mean, maybe a CMM could do it, but
right. Right, and those are all the pros and cons. That's why, Jeff, I left it alone here. But if somebody put an M in here, I have no problem with that, Jeff. So, so my solution, I left it off, but for anybody to put M's in here, I count it as a good, because I do, guys, I do put M's on my threads. But I've gotten black eyes over it too from my manufacturing engineers and our professional discussions we've had on it. So, Jeff, anything else you would like to add, or?
No, that's it. No.
Good. No, thank you for your insight. So, what do you think? Anybody? Good discussions. I liked it. Like Wendy says, challenge number 2 is going to be coming out here and building upon. So hopefully this was some value or interesting discussions. It's always challenging to do design intent and what do you put on the feature control frames and all this. And again, what are you doing? You're building a product that got to meet some requirements, right? So.
Ed, I got one more question.
Okay.
The flatness. What if the part is flexible, is it's plastic? Do you recommend putting a flatness? And I see drawings where usually they don't, but if they do, does the flatness has to always go? It has to be added to the mating part as well?
So what winds up happening, you're dealing, we have a term for that. What we call that is a non-rigid part when you're dealing with plastics, or parts that may not hold its shape due to either its size, variation. We call those non-rigid. So, and it's very typical. I mean, sheet metal, if I'm bending up a sheet metal piece, you get spring back and trying to meet the requirements. We do have controls, believe it or not. So on those types of parts, dealing with the flatness down here on those, there's a couple things you can do. Typically, you might see 2 controls down here. You might see a flatness. Now, let me go over some fundamental rules. In the fundamental rules, we talk about, if I don't say anything on a drawing, there's no notes of that. Like in this part here, these 2 parts, no, of course I didn't show you the complete drawing here, but let's say there's no notes on the drawings to tell how to restrain the part, then that means the part has to be measured in what we call free state. The only force applying to these parts would be gravity. So I have to inspect all these parts without a clamping or inducing force on them, and they got to meet these all these conditions have got to be met on this part in free state. But if this was all of a sudden a non-rigid part, they could be moving, wiggling around, can't even hold their shape. Then, in this case here, this 3 thou would have to qualify in free state, but if it's a non-rigid part, what you might see is two feature control frames here, two different flatnesses. So in this case here, I might have another flatness here, and over here, let's say it's a very loose tolerance. So I put down, I'm gonna exaggerate. Let's say I make it 1/4 of an inch, 250. And you see this modifier over here, you'll see what we call a circle F, and I apologize, circle F. That's what we call the free state modifier. The minute I see that on a drawing, I go looking for the engineering notes, because over here in my notes that I probably have something saying, hey, restrain the part in a certain condition, configuration. So I'll have a note over here restraining the part. What winds up happening is that in that case here, this tells you how bad the surface could come in. In other words, potato chipping. It can come in, look like a potato chip, 1/4 of an inch, free state. Then once I clamp this part down, I put these two bolts in, I need this surface to be flat within this restraint condition of 3 thou. That's one example. There's many examples I can control this. I had a part one time, we had cables running outside on the surface of the missile, and we had very long covers that were putting on the cover of the cables up. I got a call from the program group saying, hey, Ed, 100% failure in inspection. So I went over, I kind of laughed when I walked in when I seen these covers that were 8 feet long, and they were kind of V-shaped geometry, 2 inches, and they were twisted like a pretzel, and it was composite material. They molded it, so in the mold, that perfectly real good geometry. When it popped out of the mold, they twisted. So the drawing didn't have any restraint on it, so of course it failed every time. I said, well, we got to restrain the part. We're going to add a note, and we mimicked how the part restrained in the actual missile assembly and how we clamped it. We restrained the part. We had to build a fixture. Once we then measured the part in restraint, the covers passed all day long. So maybe that's a tip or a challenge we could do about, hey, Ed, how do you deal with parts that are non-rigid parts? Did that help? So we do have controls in GD&T in the 14.5. That's called a non-rigid part. And I got a plethora of tools in my toolbox to control those, or how to do it based on what you need. Did that help?
Yeah, that would be an interesting topic, because it's like you got to tell them how much force to put on it.
Yes. We do have a new standard coming out we're working on, ASME 14.48. It's called directional loads. So it's going to talk more detail about how do you restrain forces, what directions the forces are applied to, based on design intent. But that won't be out probably for another, if I was a gambler, man, which I'm not, probably in about 2 years. But on the new standard, ASME 14.5, we did a much better job talking to the subject of restraint conditions in the new standard, the 2018, load directions and how to restrain parts in free state. So FYI, that's in the new standard. Good questions, good questions.